Okay, then we will move toward the chapter 28, which is all related to your magnetism, and then afterwards we will move toward the atomic physics and the nuclear physics. Okay, so this is the last article, second law of thermodynamics. We will discuss about the second law of the thermodynamics, which previously we were discussing about the irreversible process and that of the entropy. And there what we have seen is that in order to solve the equations complex situations easily for the reversible process, we usually convert it into the reversible process, and then we calculate the entropy or the change in entropy for the system. So in actual, all this all the mechanisms which are happening in the universe are irreversible due to the certain parameters which cannot where the waste of energy takes place, like friction, drag force, and other things. So these are the things that make the process reversible, because once you lost the heat during the friction, obviously when you will go back toward the initial position, you will further lose the heat as the friction. So when you will reach toward your initial point, so obviously it is not possible to have the same amount of energy as you have started earlier. So there are certain phenomena that we basically ignore them or in order to avoid the complex situations. But we assume that the if you have reached to the initial stage to the minimum value, to at least comparable value, so we will say that this process is the reversible process. But in the case of the irreversible process, obviously when we want to calculate the change in entropy, we will go for the to make it reversible, so it will make our procedure quite easier, and then that entropy change entropy would be for the irreversible process. Okay, so second law again itself is an example of just hold on a second, beta. Second law of thermodynamics is basically the example of the entropy. Okay, so what we have observed so far that entropy can never decrease. Okay, it will always increase. So obviously we will see that how this statement is postulated by the second law of thermodynamics. Okay, so any question up to this point? Anyone? Is it clear to everyone? चलो चले फिर, यानी नेक्स्ट आवाज आ रही है बेटा आप लोगों को मेरी? कोई एक
Yes,
क्वेश्चन मुझे
sir.
बता।
Yes,
Yes,
sir.
yes, ठीक है। बड़ी खामोशी छाई हुई है ना, इसलिए मैं पूछ रहा हूँ बेटा। अच्छा, so here comes the second law of the thermodynamics. So these are the examples which we have done in the last lecture. So what is the second law of the thermodynamics? But before discussing the second law of the thermodynamics, we will assume ठीक है कि एक सेकंड ये एडमिट हो रहे हैं पार्टिसिपेंट्स है भी आज कम काफी. So just
Yes,
assume
sir.
this, just assume this example here. Okay, we will narrate this picture in the next, in the second of the thermodynamics. Here you can see that there is a gas enclosed within a chamber. So what in a chamber, so what is happening that when we will move some weight from the top of the surface, so obviously gas will expand. So when gas will expand, so it will, in order to maintain the temperature, it will extract the heat from the thermal reservoir, so it goes to the expanding state. So it means that now it is at volume V2, expanded volume, and lower pressure. So if we consider that this is the reversible process, so obviously we can make it reversible by adding more weight here. So it will go back toward the its initial stage, which is this one. So we will then say that this is the reversible process. So we will correlate it. जी जी
सर मतलब यहाँ वही फिनोमेना यूज हो रहा है कि एक्सपेंशन कॉजेस कूलिंग और
same
compression causes heating.
जी इसी तरह it is just like we are just taking this phenomena here. ठीक है, this figure, basically we are dealing with this figure here. Okay, isothermal process, constant temperature, and here what we are doing is that gas is going from the initial stage to the final stage. So at initial stage obviously pressure was higher, so when we remove the weight, the gas expanded. So when the gas expanded, volume expanded, while the pressure decreases. ठीक है, so in this case you can see here that at the final stage volume there is increased volume while there is a decreased pressure, as we discussed when we were dealing with the entropy here. Okay, so this is the phenomena. So now he is saying that this was the reversible process. So now consider that we have moved it back toward the initial state. Okay, so again what we have done that in the expanded form, like here in this case, we have added some weight over the top of the piston. So as a result, the piston will move in the downward direction up to this point. So what will happen that now in this case, again, volume will decrease while the pressure will increase and some heat will be moved out of the gas to the thermal reservoir. Okay. So just assume this example. Right? Clear? Is it clear, beta?
Yes, sir.
Okay. So considering this scenario here, okay, just hold on a second. In this second law of the thermodynamics, okay. So कहता है कि if we want cause the reversible process to proceed from A to B, ठीक है, change in entropy was positive. So when we moved the system, okay, कैसे move किया? At initial stage, uh, there was an initial stage I. So when we moved the weight, the gas expanded. So when the gas expanded, it moved from the initial stage to the final stage. So during that process, okay, the volume increased while the pressure decreased and the entropy of the system increased. So this was the irreversible process. So we consider that this is the positive entropy. Okay. So when we will consider that now this system has moved back to initial stage, means that now it is going back to initial stage where the volume, where there will be a decrease in the volume while and increase in the pressure. So for that purpose, so the system has to release the heat in to the thermal reservoir in order to maintain the temperature. So if we will consider that, so the overall entropy should be negative here because energy must be extracted as a heat from the gas to keep its temperature constant. Like here again, just to show the example, असल में फिगर बैकवर्ड उन्होंने दे दी है ना, तो मूव करना पड़ रहा है. Here you can see here that the system is at initial stage. This is the I stage. So when we expanded the system, ठीक है, we removed the weight in order to maintain the temperature or in order to keep the temperature constant. So it will absorb the heat from the thermal reservoir. Okay, so it has reached here, so the temperature is constant and so on. Okay, but when we have to move it back to the initial stage, so obviously in order to maintain the temperature, it will have to release the heat to the thermal reservoir. So that will make the heat negative. So as a result, the entropy can be considered as a negative. So this is the, you can say this is basically the deviation from the original statement where we said that entropy always increases, it can never decrease. So if we will consider that, so this phenomena is strong one. So but the thing is that we are not the original statement that was that the entropy change in entropy for a closed system is always positive. Okay, it will never be negative. So here we are taking only gas from where heat is extracted or the absorbed. So gas itself is not a system, closed system. Gas plus reservoir is a closed system. If we will consider only a gas, it is not a closed system. But if we will consider gas plus the thermal reservoir, then it is the closed system. So you can see that if we will consider both gas plus the reservoir, then if we will move from the system B to the A, So obviously, then how we can find out? You can see here that let Q the absolute value, which during the reversible process, the energy is transferred as a heat from the gas to the reservoir in order to maintain the temperature. Okay, so Q can be written as, so the change in entropy can be written like in this way, because why we are taking the Q negative? Obviously, we are taking it negative because it is going out of the gas. It is extracted out of the gas, and we know that when gas is extracted out of the system, it is usually written as heat is extracted out of the gas. It is written as a negative. So it is the negative Q. So when it gets absorbed by the system, it is positive. So here in the second case, obviously it is absorbed by the system during A to B process. The overall system says that in a closed system, the entropy of the uh, system increases for the reversible process and remains constant for the reversible process. So if I will add them, the entropy for the reversible process, TKG from A to B, from B to A, the total change in entropy Q over T minus Q over T would be equal to 0. So if I will take only for the irreversible process, it will be written as Q over T. So you can see here that this is this one. So the postulate can be written as that for closed system, entropy change in the entropy always increases for the reversible processes and will remain constant for the uh, reversible process. So second law of thermodynamics says that there will be a change. This is the second law of the thermodynamics, that entropy will always be greater than zero. Okay, so it is nearly equal or always be greater than the zero. It can never be negative, but in actual case, in our ideal phenomena, it will always be positive. Okay बेटा, ठीक है? Just give me a second, एक second रुकिएगा, आपने कुछ चीज पूछनी है तो पूछते हैं.
Sir,
Do you have any question?
Yes, sir.
जी.
सर ये जो द एंट्रोपी ऑफ द गैस मस्ट डिक्रीज, सर ये पॉइंट और इसके बाद जो है मुझे सही समझ नहीं आया, काइंडली एक्सप्लेन कर.
अच्छा, नहीं, entropy of a system cannot be decreased. मतलब make sure must decrease. Never use a word must decrease. Okay. Here they are just giving the example, and they are giving the example के in the previous case, let's go for the process when system goes from A to B. ठीक है, just hold on a second, we will go toward the figure here in this figure. So when the system goes from this stage to this stage, so what will happen that obviously when the gas will expand, in order to maintain the temperature, it has to absorb the heat from the thermal reservoir, isn't it? So यही नहीं होना चाहिए?
Yes, sir.
So when the heat is absorbed by the system, so we will take it as a positive. यही होता है. We always
जी
take the
sir.
Q positive when it get absorbed by the gas. So the change in entropy delta S should be equal to what? Q over T. Okay, clear? So entropy is positive here. Now come towards the second point. Comes towards the second point. Now the second point says that K. No, this is the irreversible process. So for irreversible process, entropy should be positive. Now let's suppose the process was reversible. So obviously when it was reversible, so the expanded gas should go from the this initial stage compressed state. So in this scenario, obviously when you have to compress the gas, so in order to maintain the temperature, it has to release the gas to the system.
Reservoir. Yes, sir.
Obviously, sorry, reservoir, thermal reservoir. So this Q should be negative. So entropy should be like delta S is equal to minus Q over T. Okay. So, but the thing is that here we are dealing only with the gas. We are not dealing with the reservoir. Obviously, in some one case, the reservoir is extracting the heat. In the other case, it is absorbing the heat. So overall, the total heat, if we are considering gas plus reservoir, the total entropy should be equal to zero. Okay, one is the positive, other is the negative. Plus Q over T minus Q over T. So it should be equal to zero if we are considering the reversible process, and if we are considering the closed system. Closed system means that we are dealing with the gas and the reservoir. So obviously overall entropy should be equal to zero. So the second law of the thermodynamics states that the entropy for the reversible process must remain constant, while for the irreversible process it should increase. But in it is for the ideal case, but in the actual phenomena or in the real world, so what is happening here that entropy always increases because of the different factors or the parameters. The main parameter is the friction. So you, if the piston is going from A to B point, obviously it has to move against the walls. So when it is moving against the walls, so obviously it will lose the heat due to the friction, and this heat is the wasted heat because we cannot do any useful work from this heat. So obviously entropy will increase. So here for the ideal case, he is postulating that the change in the entropy of the system remain constant for the reversible process. For the irreversible process, it will always increase. But if I will give you a question in the exams, so what will happen in the real world? It will always increase. It can never be equal to zero because it can never remain constant. So now it is clear to you.
Yes, sir.
Chalo. So now moving toward the next point, ठीक है जी, up to this point, he was telling the second law of the thermodynamics. So this is the second law of the thermodynamics, that the entropy should be greater or equal to zero here. Okay, so in the actual real world, it can never be equal to zero because it will always increase due to different process like friction, turbulence, and other processes he is mentioning here. So here he is giving the example of a rubber band, and he is asking about that you have to calculate the force due to the entropy. So obviously when we stretch the rubber band, it's just, I don't know why he has mentioned here, there is no link of this to the our example. So just for the sake of the knowledge, I will here explain what he's asking. So he's saying, okay, whenever you stretch the rubber band, you obviously feel the force that it will try to move in the inward direction. Okay. So कहता है कि why rubber band resists the stretching. ठीक है. So for that purpose, we will consider the first law of the thermodynamics. So this is the first law of the thermodynamics. So it is written in the differential form. So why it is written in the differential form? So we will observe the change or the incremental change in our जो है stretching of the rubber band. So we will say that okay, there is a small increase in the length which is equal to dx as we stretched it between the our hands. Then obviously the force from the force from the rubber band has a magnitude of f which is directed inward. So when it is just like a case of the spring here. So when you will stretch the spring, so normally how you basically represent it, you represent it by the ओके कौन सा होता है रिस्टोरिंग फोर्स आपके पास F is equal to minus kx. So why you write it as minus kx? Because it is always directing toward the inward. ठीक है. So we write it as Hooke's law जो है F is equal to minus kx. So it is just like that here, rather than written it as minus जो है F is equal to minus kx. ठीक है. Rather than writing the restoring force, here we are dealing with the work done. So work done is written in the form minus F into dx. So units of work done is Newton meter. So here we can see that it has the unit of Newton meter, or it is the directed inward. The force is directed inward. So we are taking it as a negative here. So up to this point, any question? Is it clear that why we have written it as minus ftx rather than ftx?
जी sir.
चले. Okay. So again, putting the values of the dq and d's. So dq obviously जो है we will take the value from the change in entropy. ds is equal to dq over dt आ जाएगा. ठीक है. So from where we will calculate the dq, which is equal to ds into t. So this is written it like here. So we'll put the value of dq and dw in this equation, and finally we will take the entropy as a ठीक है जी change in entropy equal to 0, change in internal energy equal to 0. So why we are assuming this? Again we are assuming this because the change in length is very small. So if it is very small, so we will consider that okay, there is not very much change in the internal energy, so we will take it as a 0. So the relation would be become like this one. So here he is saying okay, it is the force is directly related to the rate at which the rubber band entropy changes. ठीक है. So ठीक है, ये उसने एग्जांपल दी है, बट आई डोंट थिंक सो दैट इट इज क्वाइट रेलेवेंट टू योर thermodynamics. Okay, so just for the sake of knowledge, I am here demonstrating you that how he has correlated force with the entropy. So is it clear?
Yes sir.
कोई चीज up to this point
जी
पूछने
sir.
वाली? ठीक है. So next in the next case क्या किया है कि in the next example उसने थोड़ा सा इसको इस तरह किया है कि you have a coiled rubber है, rubber band. Coiled rubber band means that ठीक है, it is जो है वो in the zigzag structure है. ठीक है. So when we will make it straight, why how we will make it straight? We obviously apply some force and we will make it straight. So when it is in the zigzag form, so it is in the greater disorder. ठीक है. And when it is in this form, in the second form, it is in much ordered formation. So what is happening here that okay, when you have a greater disorderness, entropy will be higher. When you have a lesser disorderness, entropy will be smaller. So when I will give you example in the midterm exams or in the MCQs, I will ask you, okay, so entropy will have a larger value when there is a disorder, or it will have a smaller value when it is in the ordered form, in the disorder form. So your answer should be like that. Okay, when you have a disorder, more disorder, there will be larger value of the entropy. Okay, so when there is a less disorder, there will be a lesser value of the entropy. So clear beta?
जी सर, मतलब डायरेक्टली रिलेशन
जी directly. Okay. So this was your last article. ठीक है. So this is the entropy in the real world, Carnot heat engine and other things, but these are not part of your course outline. So we will move toward the chapter 28. ठीक है. So
सर मैंने क्वेश्चन पूछना था.
जी जी बेटा.
सर ये जो हम मतलब चैप्टर्स कर रहे हैं तो मतलब सिलेक्टिव टॉपिक्स हैं, तो एक्सरसाइज में भी मतलब सिलेक्टिव ही क्वेश्चंस होंगे ना?
जी बेटा, इसी तरह उसकी रीजन ये है कि मतलब दे हैव गिवन दिस कोर्स लाइन इज प्रोवाइडेड फ्रॉम योर डिपार्टमेंट, सो वी हैव टू फॉलो दिस कोर्स आउटलाइन. अदरवाइज इफ वी विल go for the whole chapter, we will not be able to cover your whole course outline. ठीक है. ठीक हो गया बेटा?
यस सर, थैंक यू.
आज के लिए बहुत है या आगे पढ़ना है आप लोगों ने? क्या कहते हैं, रोजा तो नहीं लग रहा?
सर रोजा लग गया, बच्चों को रोजा लग गया.
सर बहुत है सर.
अच्छा बहुत है बेटा.
तो काफी है आज के लिए.
सर जी वो बाकी अपलोड रिकॉर्डिंग्स अपलोड कर दीजिएगा, लास्ट रहती हैं 2-3 लेक्चर.
अच्छा सॉरी यार, मैं फिर चेक नहीं की, मेरे ज़हन में नहीं रहा, थोड़ा सा बिजी रहा हूँ, काफी ज्यादा बेटा बिजी रहा हूँ मैं. अभी भी साथ साथ ना वो एक प्रोजेक्ट जमा करवाना था, उसी में मैं बिजी था, लेकिन बहरहाल बेटा मैं कर देता हूँ. ठीक है. हाँ अच्छा, मुझे ये बताएं कल क्लास लेनी है आपने सुबह 8 से 9 या?
सर वैसे बहुत जल्दी है, मंडे वाले दिन ही रहा.
थोड़ा लेट कर ले.
अच्छा मंडे को
लेट कर लें सर.
सर जी रिक्वेस्ट है, काइंडली मंडे को ना करें, कल करनी है तो कर लें.
सर कल सर मेरे यहाँ टाइम डिफरेंस हो जाएगा, वो जुम्मे का मसला होता है, इसलिए कह रहा हूँ मंडे को.
सर कल ना करें.
कल ना करें सर.
अच्छा चलें फिर रेगुलर ही करें जो आपकी वेडनेसडे को है. ठीक है. अच्छा मुझे ये बताएं कि अगर आपको सुबह 8 से 9 कर लिया करें, कोई मसला तो नहीं है क्लासेस का?
नो सर 8 बजे रहने दें.
ओके सर जी, सुबह स्टडी के लिए भी उठते हैं
सर. अगर
8 बजे नहीं उठा जाता, 8 बजे नहीं उठा जाता.
सही बात. इसी टाइम ठीक है.
अच्छा ठीक है बेटा, ठीक है फिर, ठीक है एज इट इज. ठीक है. नेक्स्ट टाइम देयर विल बी अ क्लास ऑन वेडनेसडे. ठीक है. और I will take मतलब just I will take some extra time. ठीक है at that time, so in order to complete the leg here. ठीक है बेटा. चले. ओके टेक केयर, हैव अ नाइस टाइम बेटा, दुआओं में याद रखिएगा. ओके बेटा.
अल्लाह हाफिज.
ओके थैंक यू.
अल्लाह
हाफिज बेटा.
अल्लाह हाफिज सर.
अल्लाह हाफिज. अल्लाह हाफिज बेटा.
अल्लाह हाफिज.